Welcome to this explainer. I am absolutely thrilled to guide you through what is basically a giant cosmic detective story today. We're going to look at the universe not just as some static, pretty picture, but as a massive, actively churning machine. Specifically, we're diving into exactly how the universe builds stars. We've got the data, we've got the telescopes, and we've got this incredible deep space mystery that astrophysicists have literally been trying to crack for decades. And this profound question is really the beating heart of today's mystery. It's so easy, right, to just look up at our sun and assume it spontaneously drifted together out of some quiet, lonely cloud of gas. But modern astronomy, it points to a much more violent, chaotic, and honestly fascinating origin story. So to figure out our own origins, we're going to peer deep into a breathtaking cosmic laboratory to watch star formation happening right now in real time. All right, let's dive right in. Welcome to the scene of the crime. This is NGC 2467, which is sometimes called the Skull and Crossbones Nebula. What we're looking at is a stunning high-mass star-forming region captured in this gorgeous infrared by the SPITZER Space Telescope. And right at the heart of all this chaos is HD 64315. It's this massive, incredibly hot blue O-type star. Now, this star is part of a binary open cluster system that is firmly embedded inside something called Collinder 164. Honestly, you can think of Collinder 164 as the absolute engine of NGC 2467. The massive O-type star powering this engine is so intense, so blistering hot, that its radiation is literally carving out a giant cavity in the surrounding gas and dust. Which brings us to our central mystery, coeval versus triggered star formation. See, that massive central star acting as the engine in Collinder 164 forces us to ask a really fundamental question. How exactly are all the smaller stars in this region being born? We have to figure out which of two scenarios is actually playing out. First, we have coeval star formation. This is the idea that all the stars in a cluster, the giant ones and the tiny ones, just form in one massive spontaneous burst at the exact same time, like twins, or well, thousands of twins. Then, on the flip side, we have triggered star formation. This is the hypothesis that the older, massive stars, like our blazing engine in Collinder 164, act as a powerful catalyst. As they burr hot and expand, they literally bulldoze the surrounding gas together, triggering a sequential wave of younger stars. So, are they all siblings born together, or is the older star actually forcing the birth of the younger ones? To crack this case, astronomers couldn't just casually look through standard telescopes, because all the visible light is completely blocked by these massive, thick walls of interstellar dust. So they brought in the heavy hitters, the SPITZER Space Telescope and the Hubble Space Telescope, using them like cosmic magnifying glasses. SPITZER's mid-infrared mapping lets us peer straight through that thick dust to detect heat, while Hubble gives us these ultra-high-resolution optical details of the gas itself. Teaming up, they went hunting for the ultimate cosmic clue: hidden protostars. In the biz, these are known as young stellar objects, or YSOs, basically infant stars that are still wrapped up tight in their birth cocoons. And by analyzing the thermal glow of all that dust, researchers identified exactly 45 candidate young stellar objects in this specific mapped area. They spotted these by looking for clear mid-infrared excesses, which is just a fancy way of saying they found the distinct heat signature of a baby star warming up the little dusk disk immediately surrounding it. Finding 45 of these? That's the smoking gun right there. It proves, without a doubt, that NGC 2467 isn't just some old, retired star cluster. It is a highly active nursery with very recent, ongoing star formation. Now, what's really wild is the spatial distribution. Just look at where these baby stars are hanging out. Notice how they aren't just scattered randomly out in the open? No way. They are sitting right up against the edges of the dark molecular clumps, exactly where the advancing light and shock fronts from that massive central star are slamming into the gas. It's honestly like watching surfers riding the crust of a massive cosmic wave. This visual evidence gives us a massive hint that the big central star is totally dictating exactly where these new stars are allowed to form.
So if these stars are being triggered, how does that actually work mechanically? Well, one of the leading theories is something called the collect and collapse mechanism. Imagine the massive star in Collinder 164 acting like a colossal cosmic snowplow. As it blasts out intense radiation, it drives a massive shock front outward. This snowplow sweeps up all the ambient gas and dust, pushing it into this incredibly dense, compacted layer right along the leading edge. Eventually, this piled-up wall of gas gets so incredibly dense and heavy that it becomes gravitationally unstable. It just can't hold itself up anymore. It fragments, collapses in on itself, and boom, you have an entire brand new generation of stars.
But wait, there's actually another suspect mechanism at play here too, called radiatively driven implosion, or RDI. In this scenario, the gas isn't just swept up out of nowhere. Instead, the molecular cloud already has some thicker, pre-existing clumps of gas just kind of floating around in it. When the blistering ultraviolet radiation from our massive engine star hits these clumps, it flash heats the outer layers. This creates an insane high-pressure zone that literally crushes the clump from all sides simultaneously until the core implodes, igniting a new star. This superviolent process often leaves behind what we call cometary globules, these dense heads of gas with long, sweeping tails pointing directly away from the massive star that's doing the ionizing.
To really see this in action, focus on the red lines mapped out here. Those lines represent the expanding ionization fronts, the actual physical shock waves being driven outward by the massive stars of Collinder 164. And those little numbered markers, those are our 45 young stellar objects. When researchers mapped them all out, they'd found that these infant stars tightly hug those red expanding boundaries. I mean, they are incredibly concentrated right along the impact zones. This absolutely proves that the massive stars are actively compressing the gas to trigger new starbirth.
The researchers really hit the nail on the head with this takeaway. They explicitly noted that the YSOs are simply not randomly distributed. Over 75% of them are clustered directly at the edge of the region, right along those ionization fronts. What does that mean for us? It means the star formation here is definitively not coeval. They didn't just all pop into existence at once. It's an ongoing, triggered chain reaction. The intense, burning life of one stellar generation is actively, forcibly seeding the next.
Let's put some hard numbers on this, because astrophysicists actually calculated the total star formation rate in this entire region. Using models based on expected stellar populations, they estimate there should be about 5,000 stellar sources out there in the wider area. But when they isolate the current star formation rate, the massive payoff of this whole investigation is realizing that between 25 to 50% of all the young stars currently forming here were explicitly triggered into existence by those massive shockwaves. We're talking about a huge chunk of them. This isn't just some rare, fringe occurrence. It's a major driving mode of how the universe creates stars.
So let's bring it all home. Part 2, our cosmic origins.
Now you might be sitting there wondering, okay, cool, but what does some distant nebula have to do with us? Well, actually, this discovery is deeply personal. Scientists believe our own solar system didn't form in some quiet, peaceful, isolated corner of space. The isotopic evidence we find in our own meteorites strongly suggests that our sun originally formed in a massive, chaotic cluster environment, exactly like NGC 2467. We very likely had our own version of Collinder 164, a massive, blazing stellar neighbor that either went supernova or pushed massive shockwaves through our local gas cloud, compressing the exact material that would eventually become the sun, the Earth, and ultimately you and me. Understanding this whole triggering mechanism puts the formation of our planet into this incredibly violent, awe-inspiring new context.
So I'll leave you with this final thought. The universe is just so deeply connected. Destruction and immense, terrifying power in one corner actively create life and new beginnings in another. The next time you gaze up at the night sky, or honestly, even just feel the warmth of our sun on your face, ask yourself, is it chaotic, explosive stellar neighbor, some long-dead massive star, the only reason we are even here to wonder about it at all? Thank you so much for joining me to explore this incredible cosmic explainer. Keep wondering and definitely keep looking up.